Hello everybody. Let us start our discussion today. Last time we looked at Lorenz transformation and few of its consequences. Today we will again deal with Lorenz transformation and some more consequences. So let me first write down the Lorenz transformations for you, and let me remind you of what we mean when I say Lorenz transformation. So let us consider one reference frame, and I draw this space-time diagram to talk about the reference frame, and I give it a label, say S. Some event E is happening at this reference frame, and that event, as we know in the space-time diagram, will correspond to a point. So let us label that event in terms of C T1 and X1. So this is one event, this reference frame happening at the time T1 and position X1. I can have, so remember that how do I define this, how do I make this reference frame? There is one observer standing with that paper where the position is written, they're standing at that position, and each of them have a clock. So there are observers at each positions along X, and we are dealing with only one spatial dimension just for simplicity. There are observers in Y, Z everywhere in the space, and they all stand still. I consider another reference frame, and here again there are all these observers, but this reference frame, I say that is moving with a velocity v with respect to s. That essentially means that all the observers in this new reference frame are moving with a velocity v with respect to all the observers in the reference frame s. So in between these two, there is a v, velocity v. It's along x direction. So let me not put that x. So this is along x direction. So remember that this v is along x direction. So let's say x cap. Now the same event can also be recorded by these new set of observers. So another reference frame, call it say S prime, is really another new set of observers. And the same event E is recorded by this new set of observers at a different, so they will record different x and t, right? Lorenz transformation essentially tells us the relation between the x and t here and the x and t there. So let me bring this down a little bit so that I can write down the transformation for you on top of it. So what are the relations? X prime, or should I not write by starting Ct prime? Ct prime is Ct minus beta x times gamma. X prime is x minus beta Ct times gamma. Y prime remains as y and z prime remains as z. And remember that beta is nothing but that v by c, and gamma is 1 by root over 1 minus beta square. Let me keep things a little more organized. So I'll bring this down a little bit more. Okay. Now, you may ask the question, okay, so this is t prime, x prime, y prime, and z prime. In terms of, in the right hand side, I have t, x, y, z. What if I wanted the opposite? Means that what if I wanted to write down here in the left hand side, or ct, x, y, and z in terms of the measurements in the S prime frame? I can do that simply because what you see is that if this frame S prime has a velocity v with respect to s, it is obvious that then s will have a velocity minus v with respect to s prime. So what all I have to do is wherever I have v, I have to put minus v. So that will change beta to minus beta, and nothing else actually will change because here I have beta square in the gamma. So if I want to write the reverse transformation, then that is simple. This is just writing a plus sign here, and all x obviously in the right hand side will change to x primes. Right? So this is what we mean by Lorenz transformation. So I just wanted to keep this in your mind because this is what we are going to apply now for some more cases. Okay, so these are important things. So let me keep these in wiggly things. Remember that beta is always less than 1 because we saw yesterday in the last class that b is always less than c. And here beta comes in the denominator, which is less than 1, which means gamma is always greater than 1. Okay, so I should, when I say beta less than 1, I obviously mean modulus of beta, just because it can be negative also. So modulus of beta is less than 1. So v, I am talking about the absolute value. Okay, so beta is always less than 1, gamma is always greater than 1. It can be, gamma can be equals to 1 also if beta equals to 0. Essentially, two reference frames then will be the same one. All right, so let us start using these today. And one thing you remember, we derived in case of Galilean transformation immediately after writing it down was the velocity addition rule. And that has to change now because you remember this velocity of light or the speed of light is not supposed to change if you do a transformation in the reference frame. If I use the Galilean transformation, it will change. So let us try to figure out first what is the velocity transformation rule. Now to do that, let us look at this space-time diagram once more. Let me remove all these. This we have already understood. And let us look at what do I mean by velocity transformation. Okay, so we have a particle or a person moving with a velocity vx along the x direction. Okay, so his trajectory will look like this, as you will always, I think that by now you will agree with me that his trajectory will look like this. Okay. So this is the trajectory or the word line of a person who is moving with a constant velocity vx along x direction, of course, and you know that this is by definition is dx by dt. If I look at the same person from the other reference frame, you see the velocity between the two reference frame has to be constant because we are talking about only inertial reference frames. So this person, so what can happen to the velocity of this person? It can increase or decrease or even can go to 0. If I arrange capital V becomes minus of Vx, then it will go to 0. But in general, the velocity will change, but it will move with the constant velocity. So let me draw with another line which is a little bit different, with a different slope. So this is the velocity of that person in this reference frame Vx prime, and by definition it is how much it goes in x prime compared to how much is goes in t prime. Okay, so this is what I need. So what I want to do now is to know what is Vx prime in terms of Vx. So let's see what is dx prime in terms of dt. Well, dx prime, or let me write down first the Lorenz transformation for x. So it's x prime is, we know, is, which is written just above, x minus beta c t times gamma, right? So what will be dx prime? Dx prime, which is over here, will be dx minus beta and c. C is obviously, that's a big constant. Beta is also constant because beta is the relative velocity between the two reference frames divided by c, and relative velocity said it has to be a constant velocity. So this is also, the d will only count for the time, and gamma is also constant if beta is constant. Similarly, t prime or ct prime is ct minus beta x times gamma. So if I just calculate the differentials, it will be just this, right? And I can do a little bit algebra in the second one. I can remove c from here and here, because in this particular case that will be more useful for us. So I have to divide beta by c. Okay. Now I can calculate what is my Vx prime. It's essentially dx prime by dt prime. And how much is that? Well, we can see dx prime written over here and dt prime written over in the second line. Gamma cancels out first of all. So I can just write dx minus beta is v by c. So this I can just write v here. And in the denominator, this is dt minus, so beta is v by c. So this is now v by c squared and times dx. So this way, if I calculate Vx prime, what will I get? I take dt common from numerator and denominator. So the first thing is dx dt. So let's write it here. The first thing I get here is dx dt minus dt common. So this is just v. Here the first term becomes 1 and the second term becomes v, and then again dx dt by c squared. So dx dt, you know, is v. So this is just vx minus v by 1 minus v vx by c squared. And that's our first velocity addition rule. If you remember, for Galilean case, it just did not have the denominator. It was only, if so Galilean case, we will go back if v is much less than c. So then obviously this term I can neglect. So the denominator become 1. So in this case, I go back the Galilean velocity addition law or velocity addition rule, which you are very much familiar with from the +2 physics, right? But let's see, if it is not so, then what happens? Okay, so let us consider the case where I have a particle moving along this direction with a speed c by 2. Okay, in one reference frame, it's moving along this direction with a speed plus c by 2. And then I look at the particle from a reference frame which is moving at a speed c by 2. So you can imagine that one person moving this way with respect to me with the speed with the speed c by 2, another person moving in the right hand direction with the speed plus c by 2. So what this person will see will measure the speed of this person, or what, to be more precise, what the observers in the reference frame of, say, this called B, will measure the speed of the particle A. That's my question. Okay, so you can see in this particular case, their velocities are in opposite direction. So Vx, I can say, let's take Vx equals c by 2. So then the other V has to be minus c by 2 because they are in opposite direction. Then only they will add up, right? So if I apply simple Galilean transformation here, I will get that the velocity of A will be c, right? So I am letting them move in either direction in half the speed of light, and one will see, if I use Galilean transformation, that the other is moving with the speed c. Let's see what happened here. So it's not fun if I use c by 2. Okay, let's try with c by 2. You can try with c, where you can add up the velocities to 2c, which we have already seen is not possible. So what will be Vx prime, which is what we are up to? So it is c by 2 here. Minus of minus c by 2 makes it plus c by 2. In the denominator I get 1. Again, minus of minus c by 2 is plus c by 2. So this is plus c squared. And there is 2c by 2's. So 4 here. This. One in the numerator. Denominator, what do you get? 4 plus 1 is 5 by 4. Or I can write 5 here and 4 here. So I do not add up to c here. Do not add up to the speed of light. I add up to 4/5 of the speed of light. This is just because of the denominator. So this is how the velocity addition works in special relativity. Now we have only talked about Vx prime here. We know if I would have had a component in the velocity in y, then y doesn't change, and a component in z, obviously z also doesn't change if the speed is only along x direction. So along with this, the change in the velocity along x, I will also get change in the velocity along y and z direction. So I request you to calculate this out. It is very straightforward to calculate, exactly the same way that we have done it right now. So Vy prime will be related to Vy in the following way. 1 minus Vx V by c square. It's the same factor which was in the denominator of the previous one, but now there will be a gamma also, and Vz prime also, as you can imagine. So you see, because of the x velocity, the y and z velocity changes. What will this amount to? This is not to the power gamma. My writing was not proper, so this is times gamma. Okay, and Vx is already written. How the Vx will change is already written upstairs here, Vx prime. So what have we learned? You see, all three Vx, Vy, Vz changes. and they does not change in proportionate amount. So if I consider a vector which is the total velocity v, it has the three components, right? So if I try to draw it here, say vx here, vy here, vz there, right? And the ratio of these three components tell you which direction the vector is. The relative ratio of these components gives you the unit vector along the velocity v. And because this ratio of this component changes in case of a Lorenz transformation, it's not only that the value of the velocity will change, the velocity vector, the direction of the velocity vector will also change. Okay, so this is one consequence we have learned already of the Lorenz transformation. It's the velocity addition. So let me write it here, velocity addition. This consequence we already expected because Michelson-Small-D experiment did not work, where we used the Galilean velocity addition rule, where we used this, but it did not work. So obviously there should be other consequences also, but this is something that we had already expected. Okay, all right. So let's move in to the next interesting consequence, which you have heard many times. It's called time dilation. And don't go into the name right now. We'll understand the meaning of what it says at the end of the discussion. I guarantee you that you will understand that. Okay. So let us see that what we are trying to do here. So we have this S reference frame, and you see that the space-time diagram becomes a very, very good tool to do all these discussions. And that if we have learned very well in the last two lectures, it will be really useful right now. So this is one reference frame. In this reference frame, somebody is at rest. Okay, so it is at rest at x equals to x0, say. What will be his world line, his trajectory? We'll say that his position always remains at x0 at all time, and we have done it before, so it will be like this. Now let us say two event happens at his position. Okay, so there are two events happening at his position. One here, let's call this event 1. So this is happening at a time t1, and the position is x0, of course. And this is another event happening e2. This is event I call e2. It's happening at a different time, as you can see in the diagram, but the same position. Okay. Now these two times are measured E1 and E2, E1 and E2 measured by the same observer. Because the observer is sitting at that position x0, there's only one observer there. He is measuring these two times. Okay. Let me ask you, what type of interval is it? So remember last time we were talking about this S. So let's say S12 squared. So let's calculate the interval here. The interval is CT2 minus CT1 square. Minus x0 square is 0. So the interval is essentially S12 square is c square, and let us call the time difference delta t. So c square delta t square. Right? What type of interval is this? Well, it is obvious that in this particular case, there is no special part in the interval. It's all time and it's greater than 0. So this is a time-like interval. Okay. Now see, we are talking about two events happening in this very particular reference frame. It's happening in all reference frames, by the way, but we are measured by the observers in this particular reference frame, where only one clock is used to measure the time difference. And because only one clock is used by only one observer, there is no spatial part in the interval. The interval only has the time part. That's why this minus, there is no minus delta x square here, that is 0. So this is a very spatial reference frame where these two events happen at the same position and their time difference is measured by the same observer. So this time difference delta t, we'll write it as delta t0 and we'll call this proper time. Why do we call it proper time? Well, you see, it's a time-like interval. And remember that intervals doesn't change. The value of this S doesn't change as you change the reference frames. It's always the same that we have seen last time. And all of it is coming because of time in this particular reference frame. That's why we call this proper time. So you see, delta t0 and S12, they're essentially the same quantity multiplied by a c square only. The value of these are exactly they're essentially the same quantity. That's why we call it proper time. Proper because measured by the observers, same observer. The interval is measured in the same clock by the same observer. Okay, now let us look at the same events happening from a different reference frame. Okay, so this is x prime now, ct prime, and let's ask the question. This is the difference reference frame where the relative velocity between these two reference frames is v. Okay, which means the observers in the s prime frame are moving with respect to the observers in the s frame with a velocity v, or vice versa. The observers in the s frame are moving with a velocity v with respect to the observers in the s prime frame. So this was the trajectory of one observer in the s frame. Now that trajectory here will look something like this, which is the trajectory with constant velocity, right? So this is the same trajectory that I have drawn here. The same world line that I have drawn here is now reproduced in the s prime frame. It looks like a slant line because the s prime frame observers are moving with a velocity v with respect to s prime and vice versa. Okay, so let's now level the two events. So this is the event e1, and now I write this down, write the coordinates in terms of the measurements in the s prime frame. So I call them prime, and then e2 all right. You see, it has to be x1 prime and x2 prime now because they're definitely not happening at the same position. They're happening at different time and different positions. And if I ask you, what is x2 prime minus x1 prime by t2 prime minus t1 prime? Difference in x by difference in t. This we have seen before. This is essentially the velocity, and the velocity is v, because it's a world line of the same observer, this reference frame. All right. What is the time difference in this reference frame? Delta t prime is t2 minus t2 prime minus t1 prime. That's also nice. But you see, now these two times are not measured by the same observer, because now this happens at x1 prime. So the observer at x1 prime measured t1 prime, and this happens at x2 prime. So the observer at x2 prime measured t2 prime. So there are two different observers measuring the two events, the time of the two events. Previously in the S frame, it was measured by the same observer. So definitely this time difference is different. It is not the proper time. So let's calculate S12 here. Remember, they are same in two reference frames, both the reference frames. So here, let me start by writing shorthand. So c square t2 prime minus t1 prime whole square, which is delta t prime square. And now I also have an x part, because this is not 0. x2 and x1 are not same. This, if I manipulate a little bit, say I take c square delta t prime square common, then what I get inside is 1 minus, I get a c square in the denominator, obviously, in the second term. And then what stays at the top is x2 prime minus x1 prime square by t2 prime minus t1 prime square, which is nothing but v square. So this is v square. So this is c square delta t prime square into 1 minus v square by c square, remember, is beta square. So what do I get? This and this are same. The intervals doesn't change. That's one of the consequences of the Lorenz transformations we have seen. So this should be same as that. C square cancels out from the both sides. So delta t0, I take a, okay, let me write it square now, is delta t prime square into 1 minus beta square. Fine. Now you see, here delta t0 is a very sacrosanct number. It's the proper time, right? And it's also related to the interval. So this delta t0 is something that doesn't care about which reference frame you are. I can always get delta t0 if I divide the interval calculated in any reference frame by c square, or interval by c. Then I will get delta t0, right? So for any reference frame, if I want to know the time, so then what I should do is I can write it this way. Delta t prime is delta t 0 1 minus beta square. Or you will agree that 1 by 1 minus beta square is just gamma. So this is delta t0 times gamma. And this is the celebrated relation for time dilation. Okay. So what is it telling you? It is telling you, I know the value of the interval, so I know the value of delta t0. That is essentially the time taken between these two events where these two events happen at the same position. So if you wish, this is the, say, the birth and the death of me, then I have to be still all the time. With respect to me, I am always still. So it's the birth and the death measured in my own reference frame, or that's also called sometimes rest frame, in my rest frame. So delta t0 is the proper time which is measured in my rest frame. If anybody else see me moving with a constant velocity v, my lifetime measured by that person will be different, and that will be different by a factor of gamma. You will measure the lifetime to be larger, because remember that gamma is always greater than 1. Gamma is always greater than 1. Okay, so time, that's why it's called time dilation, because it's like you are waiting for a train and the train is not coming. So you feel that the time is moving very slowly, and that's why it's called time dilation. Okay, so the time that you measure between two events happening in the trajectory of a particle which is moving with a velocity v is the proper time interval between these two events, which is the time difference measured in the rest frame of the particle times gamma coming from the relative velocity between you and the particle. Okay, now you may think that it's a hypothetical case, but let me give you a concrete example where it is seen. Where it is seen is very clearly and can be explained only using time dilation is for the case of a subatomic particle. Mu1. It's also let me, I made it hybrid a little bit, so let me correct myself. The particle is called mu1, M-U-O-N. Okay, sometimes it is written with a mu, the Greek letter mu. Now it is known from calculation and also from experiments in our labs that mu1 has a lifetime of around 2 microsecond. Okay, so this is measured in the rest frame of mu1. So let's call that it's the lifetime of mu1. So let us write it this way: delta t mu, delta t suffix mu is 2 into 10 to the minus 6 second. Okay, so now if I consider, so this particles are produced from cosmic rays. So if this is our earth, there is this very feeble atmosphere on top of the earth, and it has been seen using balloon experiments. So people used to send balloons up and measure the existence of different particles. Seen that it is produced in the upper atmosphere around, say, 10 kilometer up. Okay, it is produced there. Okay, so it is produced there, and we know that it has a lifetime of 2 into 10 to the minus 6 second. What does it mean? It means it is produced through some nuclear reaction. It will live for only 2 microsecond, and after that it will disintegrate to some other particles. Okay, all right. Then you have also this cosmic ray observatories on the top of the mountain, and we know that obviously Everest is like almost 10 kilometer high, 9 kilometer high, but most of the mountains where you can put in things are like 4 kilometer high. So the top of the mountain where you have these cosmic ray observatories are 4 kilometer up. Now, a particle which is produced at 10 kilometer are also found at these observatories. So it has traveled 6 kilometers down. Okay. Now, if I say, okay, so delta tau is the time it leaves, and say they're traveling at a speed, at a speed, so say v mu 1 is almost the speed of light. So let's say 0.995 times the speed of light, almost the speed of light. So you can take it for the timing, you can take it as 1. Okay, so let's see how much distance will it be able to travel. So it will be able to travel, the distance the mu1 will travel will be, okay, so let's take this c for the timing. So 3 into 10 to the 8 meter per second times this many seconds, 10 to the minus 6. So this much meters it will be able to travel, which is only 600 meters. So it's produced here at the upper atmosphere. It will only can count down 600 meters before it disintegrates, but it is still found 6 kilometers away. How is that possible? It's possible because of time dilation. Because this is the lifetime measured in the muon's reference frame. So it's a proper lifetime of the muon. The lifetime of the muon that we will see is not that, but it is given by 1 by 1 minus root over, I'm putting in gamma over here, 0.995 whole square, right? So I was supposed to put beta square over here. Beta is v by c whole square. C cancels out, so v is 0.995, so that's what I have put in here. And then if I multiply it by c, that is the distance travel, that will be the distance travel. If you calculate this, it will come out, you will see that it comes out to be 6 kilometers. And that's what explains these observations. Okay, so that's time dilation in action. There are many other cases where time dilation has been observed and been used to explain things, but this is one real case that we have discussed. Okay, so before we leave today, we'll discuss one more example of, or one more consequence of the Lorenz transformation. And again, I will write the name here, but the name will come live at the end of the discussion. It's called length contraction. And please follow the logical developments that we are discussing here. If you don't get it once, run the video many times before you get it. Because most of the times, these things are confused like hell, even in many books. Only if you go through the logical discussions very carefully, it will never be confusing for you. The clue here in the time dilation to remember is that the proper time is measured by the same observer. That's why it's called proper. It's measured in the frame where that observer is at rest, or these two events are happening at the same position. Okay. So let's come to length contraction, and let's ask the question, how do I measure the length of a rod? This is a very, very important point for the length contraction, which is often not stated, and all the confusion arises from that. If I want to measure the length of a rod, length that is moving in a reference frame, is to be measured. Okay, so that is my goal. So let me draw space-time diagram for this. So I have this reference frame. So I draw the S prime frame first now. And there is a rod. So at t equals to 0, say these are the two ends of the rods. So say x left, x right, left hand and right hand. And it's moving with a velocity v in this reference frame. As I said that it's a moving in this reference frame. So as we know that the left end will have a trajectory like this, the right end will have a trajectory like this. Obviously, two ends of the rod will move with the same velocity. There is no other way, right? Now imagine you are given the task to measure the length of this. Can I measure the left end at one time and the right end at the other time? So say I measure the left end. So I don't want to do this, but say just for the sake of the understanding, say the observers who is in this word line measure the left end of the rod, and later this observer measures the right end of the rod. And they'll measure this as the length of the rod. Will that be the right thing? Obviously no, right? Two ends of the rod has to be measured at the same time. Otherwise, if you measure the right end many times later, you can find a rod end up finding a rod which is very large. So two ends of the rod has to be measured. This is the most important point. At the same time. Okay, so I have done a mistake, but let me correct it. So let me remove all these from here, just not to confuse you much with these drawings. So this should not be done, so that's why I'm removing this, and I can put back things. Okay, so how should I do the measurements? I should do at the same time. So you know that we have discussed same time means there should be a horizontal line because the time doesn't change along this horizontal line. Okay, so this is the measurement of the left end, this is the measurement of the right end. So the left end measurement, let's write it here. So let's call it EL. The event of the left hand measurement is EL. And what is that? So EL is CT prime. So let me write CT prime because that will be the same for both of them. And XL. And E right, the event is CT prime again, same time, but XR prime. So this should be prime. Okay, so these are the two events. Now, this is the S prime frame. So let's come to a reference frame where the rod is at rest. Okay, and you will see again such frames where the rod is at rest is kind of special, and we'll see. We'll discuss why. So we call it S as always, and the rod is at rest, which means the two ends will have trajectories or word line like this. So this again can confuse you. So let me not write XL XR here. This should be written as L and R. It is just denoting the left and right end of the rod. Okay. Now, in this reference frame, in the S frame, is special. Why? Because you see, in this reference frame, whenever I do the measurements, it really doesn't matter. I even don't need to make the two measurements at the same time because the rod sits there. So this end and this end, if I measure at two different times, then also I get the same length for the rod. See, if I measure one here and the other time there, if I take the difference in the position, I will get the same length of the rod, right? In fact, if I consider these two events, they happen along these two trajectories, of course, but they are the trajectories of the two ends of the rod. So one event you will see that is happening somewhere here, and the other event will not happen at the same time, because remember that they are spatially separated events. If I ask you what is this interval, this you will immediately say that the interval here is space-like. Interval is space-like. There is no time part of the interval here itself at all. So if I even calculate, let us not calculate the interval. You can calculate the interval. It's just minus xr minus xl whole square, but that's all right. So here also, so these two space-like separated intervals, two events happening at two ends, they'll not be simultaneous in the other reference frame. That's why I've drawn them at two different points. But that really doesn't matter, because in this reference frame, wherever I measure the left end and the right end of the rod, they will remain at the same place. So these two events, EL, now I will say that it has a coordinate CT1 prime and XL here, sorry, not CT1 prime, but CT1 and XL for this left end, and here it is CT2 and XR. Okay. So let us ask the question that what is the length of the rod now measured by these two reference frames? In this reference frame, in the right hand side case, I get a length which is obviously XR prime minus XL prime. In the left case, where the rod is stationary, I get a length which is XR minus XL. But you see, again, this reference frame is special because these two measurements can happen at any time. And this is a reference frame where the rod is at rest. So this length we call again with L0, which is proper or rest length of the rod. Okay. So what is the relation between L0 and L? Well, L0 is XR minus XL, and now I can write XR in using Lorenz transformation. XR will be XR prime minus C T prime, which is here, times gamma minus XL prime minus CT prime. The same T prime, remember, the measurements in S prime frame happen at the same time, and there is no gamma prime obviously. And you will see that this cancels out with that. I'm left with XR prime minus XL prime times gamma, which is XR minus XL is nothing but L times gamma. So L0 is a special length. L, which is the length measured in a reference frame where the rod is moving with a velocity v, is given by L0, which is its proper length, divided by gamma. And this is the celebrated relation of length contraction. You see, it's a contraction because gamma is always greater than 1. So in all reference frame where the rod is moving with a certain velocity, its length will be smaller. That's why it's called length contraction. Okay. Smaller compared to its length in the frame where it is at rest. If you ask the question, what happens instead of a rod in this frame if I had like a paper or even a parallelepiped like this? So it's moving in this direction x, but it has a length in x, a length in y, and a length in z. Okay. So you will see Lx will change from its proper value by the transformation relation. Ly and Lz will not change. Why? Simply because if you look at the Lorenz transformation relations, y and z remains the same. So there will be no length contraction along y and z, but along Lx there will be a length contraction if the velocity is along x. Or better to say, there will be a contraction along the direction of motion of the rod or of the object. And this also means that the density, mass density of the object will change. And you can think about it. We'll stop here. Today what we have seen length contraction, we have seen time dilation, and we have derived the rules for the velocity addition. That's it for today. Thank you.